This is Unit 4, Video 13. In this last video, we will talk about special types of decomposition reactions. In the previous video, we talked about special types of synthesis reactions, and a lot of these will be simply the opposite, the flipped version of what we saw above. Now, bases, in our case, our bases are metal hydroxides, like sodium hydroxide. When heated, remember this is a heat symbol, will decompose into sodium oxide and water. Previously, we've seen that metal oxides plus water give you metal hydroxides. This is just the flipped version of the same thing. And again, you can put any metal in here you want. You can put magnesium, calcium, copper, and the same reaction will result. This does require heat. It will not happen on its own. If you just have sodium hydroxide sitting in a bottle, it will not decompose into water and sodium oxide. You have to apply quite a bit of heat for this to happen. And then acids do a similar reaction. Here you have carbonic acid. They will decompose into the nonmetal oxide and water. We saw how nonmetal oxides plus water give you acids, but here it's just the same thing but reverse. So here it says accept state symbols on the hydroxide. So if you take a look, hydroxides previously, what we saw is a solid with water gave you aqueous. Our metal hydroxide was aqueous. However, here we have a metal hydroxide that's solid. So it turns out you can actually begin with a solid and do the same thing. If the water had been evaporated, the metal hydroxide remains, is the idea. Alright? Now, we can also decompose other compounds besides just hydroxides. We can, for example, decompose carbonates. Now, carbonates famously decompose into carbon dioxide gas. They actually release carbon dioxide gas. So in here, in any carbonate really, is hidden CO2 gas. Actually, the way it got there was it was added to a metal oxide. So when you heat a carbonate, it will decompose and give off CO2. Now what will be left over is the metal oxide, the oxide of that metal. And again, you can substitute calcium for magnesium, for copper, for really any metal you would like, and it will release carbon dioxide gas and give you the metal oxide that results. And then chlorates also do a similar decomposition reaction, except chlorates are famous for producing just oxygen. So you can actually produce pure oxygen just by decomposing a chlorate. So here is potassium chlorate, which is heated. Again, for both of these you would need some heat to give you, now in this case, when all the oxygen leaves, all this oxygen is gone, what you're left with is just the potassium chloride. Now you say, well, there are 3 oxygens here and only 2 left. Well, that's because the equation is unbalanced. If you balance the equation, you'll see that you began actually with 2 potassium chlorates, you got 2 potassium chlorides and 3 moles of oxygen. And in this case, for a total of 6 oxygens, here, and you have 6 oxygens that initially left. So you actually release all the oxygen gas. So be able to do a few of these. Let's actually try 1 or 2 of them. We can do both problems here. Write the balanced equation, chemical equation, for the thermal decomposition of copper to carbonate. Thermal decomposition is a fancy word for saying you're going to heat this and it's going to decompose. Right, so copper to carbonate is written as CuCO3. There are 2 types of copper. This is copper 2. We're going to draw the arrow, a little heat symbol above, showing that we are decomposing by heating, and carbonates release carbon dioxide. That's what you're realizing here. What's left then is copper oxide. Now, copper by itself will not be left, so this won't be like the previous example. Rather I should say, you don't expect these to decompose into elemental metals. They're actually going to leave behind a salt. So all these special types of decompositions leave behind a salt, in this case copper oxide. You won't just get pure copper metal out of it. It's actually not that easy. The problem with getting pure copper metal is because you're heating it really, really hot, the copper will react with the surrounding oxygen either way. And that's why you have copper oxide that's left behind. The equation is actually balanced as it is, so no need to balance it. And you have a solid, usually because you're beginning with an ionic compound, you got a solid, and copper oxide is still a solid, and carbon dioxide, we all know, is a gas. And those would be the state symbols. If we do The practice problem, write the balanced chemical equation for the thermal decomposition of magnesium chlorate. Let's do the same thing. Remember, chlorate is ClO3 with a -1 charge. So we got magnesium, which is a +2 charge, which requires 2 chlorates to balance it. It should look like this. And then we're heating this up. And in the case of chlorates, chlorates actually release oxygen gas. And what you're left with here is magnesium chloride. Notice the salt. Make sure you write magnesium chloride as MgCl2. And in both cases, you don't just get the pure metal. You won't get just pure magnesium out of this. Pure magnesium is too reactive. It'll just soak up, so it will not be elemental, the same way how copper was not elemental. All right, this one does need balancing. And since we have let's see, we got 3 oxygens. Oh, we have 6 oxygens on the left, we need 6 on the right, and that should do it. Yep, that should take care of it. And state symbols, you begin with a solid. All ionic compounds are solids. In this case, you end up with a solid, and you get a gas that comes out of it. All right, so chlorates will decompose in this manner. Let's wrap up by just showing you some more complex chemical reactions. So you realize these get more and more complex, and here are a few examples. So you can actually combine like a double replacement reaction with a decomposition reaction, and this is oftentimes what happens if you put an acid with a carbonate. This is a good one to know because this actually happens in nature quite a bit. If acid falls on some sort of carbonate, sometimes just limestone, it actually eats away at the limestone and creates big holes in the ground. This is how we get caves in nature. Caves are produced through this process, through this reaction. The acid essentially comes from rainwater. It's a weak acid, but over time it eats away into pretty big holes in the ground. So an acid with a metal carbonate will give you that metal, salt, water, and carbon dioxide gas. Now the way to see this as a double replacement reaction and a decomposition reaction is first to think of these two double replacing. So if you double replace hydrogen and sodium, what you get is you get essentially sodium bromide, and then you get H2CO3, which is carbonic acid. Now sodium bromide you can see is here, but the H2CO3 are these two products. Because further, H2CO3 will decompose, this is an acid essentially, that will decompose into water and carbon dioxide gas. In other words, into the nonmetal oxide and water. So this is how it decomposes into CO2 and H2O. So this separate reaction we've just seen, this is just an acid decomposing, and so essentially you're combining the two together. And if you put the two together, these really are the 3 products that result. You don't get the 2 double replacement products, because essentially H2CO3 decomposes further down. So hopefully this makes sense how this is done. The most complex one I'll show you that is difficult to see unless you break it apart and look at it as a single replacement and a synthesis put together is chlorine gas added to water. Now this actually happens in pool water. So anytime they need to disinfect water, they'll actually do this. Either water that we have running through our houses or in a pool. You can actually put chlorine into water, and the chlorine produces, believe it or not, hydrochloric acid, and this guy here, HOCl, is actually hypochlorous acid. The way to look at it is think of the 2 chlorines here and think of water as HOH. Effectively what the 2 chlorines will do, one of the chlorines will come in and replace this hydrogen. And there you will get yourself ClOH. Now that's this product right here. ClOH is the same thing as HOCl. Hopefully you can see what happens. In other words, if this happens, you get yourself ClOH, and we just flipped it around here and called it HOCl because we always put the hydrogen in front. And then if you have the other chlorine that comes in and actually bumps out the oxygen, you have yourself HCl. So in that case, the other chlorine gets you ClH or HCl. So hopefully you can see this more or less. Don't worry too much if you can't see it. This will be an equation that you may show up a little bit, but probably won't. I won't require it. All right, so this kind of wraps up. There are more complex reactions that we can go ahead and get into, but this is enough for one chapter. We'll wrap up chapter Unit 4, Video 13.